Please unmute yourself.
Me, myself?
No. Am I audible now?
Yeah, you
Yes.
are audible. You can go ahead. Please go ahead.
Sorry.
Share your screen. Perfect.
Is it visible?
Yeah, it's
okay.
visible.
Good evening, everyone. Thank you very much to the organizers for giving me this opportunity to talk about our recent work on measurement-induced subradiance. So this work is jointly done with our GRF student Aditi and my supervisor Prasanna. This will be briefly the outline of my talk. I'll start by defining what subradiance states are and why they are significant, and what are the challenges in preparation, and the method we are proposing and how it stands out, and some key results. So let me begin. So if we look at the spontaneous emission from independent atoms, then the photon emission rate decays exponentially with time. That is, the excitation from the atom is decayed exponentially in time. But if you pack the atoms in a very small volume, then the emission from each atom interferes with each other, and the whole system behaves as a collective dipole. So then this interference forms interesting collective states. So if the interference is constructive, then what we get is called super radiance, where the emission or the excitation is emptied out in a very short time with a huge burst of light, where the photon emission rate goes beyond or above 1. But if the emission from the atoms interferes destructively, then what we get is called subradiance or subradiance states. So interestingly, these states have theoretically nearly zero decay rate, and practically the lifetime of these states is very long. That is, these states will be very important for preserving the excitation, or it will act as a photon storage. So the dynamics of this collective system is described by the collective spontaneous emission master equation. When you have finite interatomic distances between the atoms, then the equation takes this form, where HI represents the coherent dipole-dipole interaction energy between the atoms, and the dissipative part or the collective spontaneous emission part is this one. But if you place the atoms in one position, the system follows perfect permutational symmetry, and the dissipative operator becomes collective. Then the equation takes this form. Why subradiant states are important? Some application that I'll be quoting here. In a recent work, it was shown that subradiant states are very useful for quantum sensing. How? So they show that the system they have is, if you couple two-level system into with a 1D waveguide and send some input laser light and look at the output light, then the transmittance spectra is very sensitive to the detuning of the laser light with that of the atom. So subradiant states show this sharp feature in the transmittance spectra. So this delta acts as a knob here, and uh, we, this is how they demonstrate that these states will be very important for sensing. And also there are other works which show that the decay rate is very small for different geometries, and thus it can be used as a photon storage device. Yes. Is there any question?
No, there is no question. You can go ahead, please.
Okay. Yeah. So why subradiant states are hard to prepare? The collective states of atoms can be described using this total angular momentum states, where this J equal n by 2, the full J equal n by 2 represents a perfectly permutationally symmetric ladder, and the other ones represents antisymmetric states, or rather the states which does not satisfy permutation symmetry. Now the states that we want to prepare lies in this blue block here, and what happens is, when you have small super radiance from a or natural collective spontaneous emission, the excitation decays through this orange ladder here and does not go to this ladder at all. But this is for the perfect case. But if you have finite interatomic distance between the atoms, then the excitation does go through this green block here. But through the master equation, this green block is already connected to the ground state. Thus, it ultimately decays back to the ground state, and we cannot store excitation into these blue states. So there has been so also one point here that these states are uh, annihilated by the collective dissipation operator S minus. Yeah. So the existing methods uses so preparation using so sorry, in a recent experiment, it was shown that so they use superconducting qubits inside a cavity, and what they do is they using a structured driving field, they locally control phases of each qubit, and in that way they prepare subradiant states. So here, if the local phase of the driving is set to 0, then you get this plus state, and if it is if the relative phase is pi, then we get the minus state or subradiant state. But this method is very demanding, experimentally demanding for a many body array, because you have to control phases of each qubit manually, and also you have to prepare a structured drive like this. So what we propose is you can prepare subradiant state just by doing measurement on one qubit. So to illustrate our method using using two qubits, if you take two qubits in a fully excited state, uh, through spontaneous emission, if when it emits one atom, it goes to this bright state Eg plus G. And now if you say do a measurement on the first qubit, say in sigma Z basis, then the outcomes you get will be Eg and Ge. So, sorry, you can already see that this Eg and Ge will be a combination of this psi plus and psi minus. This already guarantees that in 50% of the trajectories with just one measurement, we can prepare the subradiant states or dark states. So our first set of results are for this perfectly permutationally symmetric case where the dissipator is this collective S minus. So with one measurement, we show that this graph is steady state subradiant population versus the measurement time. And with just one sigma Z measurement, we can see that for large N, in 40% of the trajectories, we can prepare these states. And with one sigma X measurement, in 50% of the trajectories, we can prepare these states. And the state that is prepared in the steady state has this form. This we analytically derive, and also this PSS sub can be analytically derived. Now, moving on to the case where you have finite interatomic distance, then what we observe is just one measurement cannot sustain steady state population, but multiple measurements can. So this result on the right hand side is for multiple measurement. So what we do here is we keep measuring one of the qubits, and since this is perturbed many times, we ask the question, do we prepare an entangled state in the rest of the qubits? So we look at the subradiant population of the other n-1 qubits, and what we see is it does go to a subradiant state in 60% of the trajectories. We also compare the performance of our method with driving. So here we apply driving on one qubit, the qubit in the other case that we were measuring, and ask what will be the purity of the entangled state that is getting prepared. So what we see is that for the measurement case, we prepare a pure entangled state, but with driving, we prepare a mixed entangled state. So this purity here represents the mixedness of the state. So these were the key results. And why our method stands out is that you don't need to control each qubit separately. You can just keep measuring one qubit, and that simplifies the experimental complications. And yeah, so thank you. Questions?
Yeah, thank you, Ipsita, for your nice talk. I think now it's the time for the questions from the audience. Any questions from the audience?
You can unmute and ask questions. Alternatively, you can also type in the chat room.
Yeah, yeah.
There are many questions in the chat room, so we can see chat room also.
Yeah.
So how can I access the chat room from here?
Are you on you are on laptop or?
Yes.
I think chat will be, I think, on the below. You will see. You will
Okay,
see some.
I see.
Yeah.
So
Any questions from the audience, please?
Can
We have to-
subroutine states actually outperform conventional coherent states in quantum sensing, or does their reduced emission inherently limit their usefulness as probes? That's a very good question. So I don't know what is the maybe performance is compared using Fisher information, I'm guessing. And I don't think reduced emission would limit their usefulness, but it is more of a fact that you get this very sharp response. So if you elaborate what kind of response to the probe you get for coherent states, then I'll be able to clarify like how the performance is different in both cases.
Any other questions? Okay, thank you, Ipsita, for your nice talk. So now you can unshare your screen, and now we are moving to the next speaker. So our next speaker is from Department of Physics, Guru Nanak Dev University, and his name is her name is Himani Thakur. So she is going to talk about atomic coherence driven optical phenomena in alkali atomic ensembles. So she is going to elaborate on it. So we are a little bit less understood on it. So are you there, Himani? Himani?
Himani, please unmute yourself.
Himani, unmute. You can unmute yourself and you can
Am
go
I
ahead.
audible, sir?
Sure, you are.
Yes, you are.
Okay, just a minute.
Yeah.
I'm unable to share my screen.
There will be an icon below for the
With the
sharing.
arrow. Now you are sharing. Means it's already you are sharing.
Yeah.
Okay, thank you. Okay. So, good evening, everyone. Am I audible, sir?
Yeah, sure. You go ahead.
Everything
Is
is
the screen
perfect.
visible?
Absolutely.
Okay. Shall I start? Okay.
Yeah, you start.
Good evening, everyone. I'm Himani Thakur from the Department of Physics, Guru Nanak Dev University, Amritsar. Today, I will present my work on atomic coherence-driven optical phenomena in alkali atomic ensembles. So, this is the outline of my presentation. I will begin with atomic coherence, then atom-light interaction, then discuss electromagnetically induced transparency, followed by atomic localization, our proposed approach, results, and finally the conclusion. So when light interacts with atom, the electromagnetic field causes the electron to oscillate, which modifies the atomic energy levels. So in the development of atom light interaction, three different approaches are used to model it. And these are classical, semi-classical, and purely quantum model. So in the classical model, the light and atom are conceived as electromagnetic wave, and these are purely classical. On the other hand, the semi-classical model, atoms are treated as quantized and light as an electromagnetic wave. And for the fully quantum model, it is usually applied quantum mechanics on both atom and light. So in my work, I use the semi-classical model due to its easiness while modeling the experimental conditions. Atomic coherence refers to the phase correlation between quantum state. This coherence leads to quantum interference where multiple transition pathways interfere with each other, and the quantum interference can be constructive and destructive, similar to the case of classical waves. So overall, coherence enables interference, and interference allows control of light matter interaction. So first, we consider a two-level system. Field-induced coherence leads to oscillatory population transfer between the ground and the excited state. The frequency related to these states are oscillatory, shows the oscillatory behavior, and these are known as the Free frequency. So the atom absorbs photon from the fields only when the field frequency is close to the atomic resonant frequency. Now, when we move to three-level atomic system, there are possible three types of three-level system. First one is lambda type, then cascade, and then is V type system. Here we use two fields, a weak probe field to measure response and a control field to modify the system. Next, one important phenomenon related to atom light interaction is electromagnetically induced transparency, which we used in our study. So here the probe field is used for the purpose of optical response investigation of atomic media, and it doesn't perturb the atomic system, while the control field perturbs the atomic system in order to modify the optical response of the atomic medium. So in the weak probe and strong field regimes, the resonant probe field passes without being absorbed in the atomic medium when the two photon resonance condition matches. So this is known as electromagnetically induced transparency. And further, this figure shows a three-level atomic system. A weak probe field is applied between levels 1 and 3, and a strong field between 2 and 3. Normally the probe field excites the atom to the excited state, so it get absorbed, but when the control field is applied, it create coherence between the states and leading to quantum interference. This figure represents the concept of trace states. When the strong control fields interacts with the atom, it modifies the energy level. Instead of a single excited state, it splits it into two new states, which are called as rest states. Because of this splitting, the probe field now interact with two pathways, and these pathways interfere destructively, which cancel absorptions. Now, this figure shows the absorption versus optical frequency. The blue dashed curve here represents absorption when the control field is off, which shows strong absorption peak. This is for the case when control field is not present. And the red curve represents when the control field is on. A dip appears here. This dip is called the transparency window. So even though the medium is normally absorbing, it becomes transparent due to quantum interference, and this is EIT. So the density metric formalism for all these results are this. The first equation shows the density matrix, and here the Pn is the probability of the system being in the state n. It gives complete information about the quantum system. In the matrix form, the diagonal elements like rho GG, rho E1, E1, and rho E2, E2 represent population of states. while off-diagonal elements represent coherence term. So these coherence terms are responsible for quantum interference effects. Now, the time evolution of the density matrix is given by this equation. The first term represents the atom-light interaction between through the Hamiltonian, and the second term represent decay or relaxation processes. So this equation describes both coherent evolution and decay effects. Next is the Hamiltonian. Hamiltonian represent interaction between atoms and fields, where omega p is the probe field strength and omega c is the control field strength, and delta p and delta c are probe and control detuning respectively. It describes how energy level are coupled by probe and control fields. So decay matrix represent here, the decay matrix represent the spontaneous emission from the excited states. This diagram shows a three-level system, which I have already discussed. Next is the density matrix formalism, and in this equation, we apply the probe field weak probe approximation, where almost all atoms remains in ground state, and which is shown by rho gz equals to 1, and rho and all the excited state population are very small, so we designated e1 row e1 and row e2 with 0, and this simplifies the equation and allow us to study the response without disturbing it. We also applied the steady state condition where time derivative becomes 0. This means the system has reached equilibrium and doesn't change with time. The this From all these conditions, we obtain an analytical expression rho e1g, which represent the coherence between ground and excited state. So the imaginary part of this equation, of the coherence equation, gives the probe absorption, which is used to study atom localization. And next, I will discuss this figure. This figure show probe absorption versus detuning. Here, the black curve is without control field, which shows single peak absorption, and the blue curve is with control field. This blue curve split into two peaks. A dip appears at the center, and this is EIT. Next graph shows dispersion versus detuning. Here, the without control field. Here, the black curve describe the case without control field. This show the smooth gradation, and with control field, a very steep slope near resonance is observed. This steep dispersion is responsible for slow light and optical storage. So, due to control field, destructive quantum interference suppress absorption, and the medium become transparent at resonance. This is EIT. So, next, this slide explains the basic idea of atom localization using EIT. If the control field forms a standing wave, the atom-light interaction becomes position dependent, and we can determine the position of the atom. Here, this is a three-level system, and here the probe field connects G to E1, and control field from E1 to E2. So now, instead of a simple control field, we use a standing wave control field, which varies with position. The control field here is written as this. This means the field strength changes with position x, and we define a filter function fx, which is proportional to the imaginary part of coherence. This represents the probe absorption at different positions. This diagram shows that probe absorption becomes spatially dependent, and so instead of uniform absorption, the atom absorb light only at a specific position within one wavelength. This graph shows the filter function versus position, and the peak represent position where the absorption is maxima. These peaks indicates where the atom is mostly likely to be found. Now, blue curve show the broader peaks, which means less precise atom localization, and the red curve here shows the very sharp peak, which means high precision localization. So, sharper peak means better localization accuracy, and so by measuring the position dependent probe absorption, we can determine the atom's position with sub-wavelength precision. So the basic principle of our work, where we extend atom localization to higher dimension and study how different parameter affects localization precision. And uh, in this case, we study atom localization to determine the position of atom even beyond the diffraction limit of light. So basically, in normal optics, we can't localize objects smaller than the wavelength of light. But using quantum interference like EIT, we can achieve sub-wavelength localization. We can locate atoms with precision much smaller than lambda, and it helps us understand fundamental physics like coherence, interference, atomic transitions in a position-dependent way. So in my research work, we study 2D and 3D atom localization in a microwave and radio frequency driven system. Our goal is to achieve high precision localization in sub-wavelength regimes. The motivation is to achieve sub-wavelength and atom localization using quantum coherence and to understand the system using rest states. And the aim is to study the effect of microwave and radio frequency fields on 2D and 3D atom localization in delta and inverter delta type atomic system. Now I will explain the theoretical model used in our work. We consider a four-level atomic system which consists of states G1, G2, E1, and E2. This system form a combined delta and inverter delta configuration, which is why we call it a delta and inverter delta system. A weak probe field drives the transition between G2 and E1. Additionally, we introduce a microwave field between the two ground states and the radio frequency field between the two excited states. These additional fields create a closed loop interaction, which is very important because it introduces phase dependent quantum interference. Uh, Now, the key idea behind atom localization come from the making the interaction position dependent. This is achieved by using standing wave field. In the 2D case, two-dimensional case, the control field is expressed as this. This means the field intensity varies sinusoidally along x and y direction, and in 3D case, we extend this idea by variation along the z direction. Now, to actually determine the position of the atom, we define a filter function, which is directly related to the probe absorption spectra. And this is for the 2D case, and for the 3D case, it similarly depends on x, y, z. Now, if this part is greater than 0, we get absorption, and if it is less than 0, we get gain. This means the probe will either loses energy or gain energy depending on the atomic response. Now, the position where the filter function show maximum absorption or gain correspond to the most probable location of atoms. Peak position define where the atom is located, and the number of peaks define the probability of finding atom. Width of peak define the precision of localization. Now I will discuss the effect of probe field detuning on 2D atom localization. Here we analyze how the localization pattern changes as we vary the probe detuning. For the case 1, when delta P is 0 at resonance, the localization shows a cross-like structure. The absorption maximum are distributed along the diagonal regions, and in which indicating that the beam which indicating that the atom has multiple probable positions. Now when we increase the detuning to 6 gamma, the pattern transform into a crater like structure. Here the atom is most likely to be found along the circular regions, and localization becomes more defined. And for the case when we substitute delta p 11 gamma, this reduces the size of the crater, and this indicates an improvement in localization precision. Now finally at delta p 15.5 gamma, the pattern becomes a sharp structure, sharp spike-like structure, and this corresponds to very high spatial resolution and 100% probability of finding the atom at a specific position at this tip. So by increasing probability tuning, we can significantly enhance the precision of atom localization. This behavior occurs because detuning changes the resonance condition between rest states, which shifts the absorption maxima in space. Now, the second figure defines the density plot with same parameters. And to understand the physical phenomena behind the effect of probe detuning on atom localization, we will discuss the rest state analysis. These firstly, this equation shows the biquadratic polynomial using the allowed transition energies between rest states, and here the roots lambda 1, lambda 2, lambda 3, and lambda 4 correspond to the energy difference between rest states given by transition between ground and excited rest levels, and these represent all possible probe induced transition between rest states. This figure shows the variation of the polynomial function with respect to the position and probe detuning. The intersection of this surface, this intersection shows the variation of the polynomial function with respect to position and probe detuning. The intersection of this surface with plane f lambda dash gives the allowed transition conditions. This intersection corresponds to the position where probe absorption becomes maximum. So clearly this means that the atom will be localized at position where the condition sin x, sin kx plus sin ky satisfies the resonance condition. Different points A, B, C, D shows the cross-like pattern, crater, and sharp spike-like localization in case of rest state analysis. So this figure provides a theoretical prediction of a localization position based on rest state energy transitions. Next is a case is the case of effect of probe detuning on 3D atom localization. This is also shows the same phenomena, and the results are same, but this in this case the results are for the 3D atom localization, and this is for the case when we vary the standing coupling strength of standing wave field, and this is for the 3D localization. And last, I will explain the effect of phase on the atom localization, which is I have already discussed in the last part also. Now, in this case, the relative phase factors are the phi 1 and phi 2. These phases arise due to the presence of microwave and radio frequency fields, which form a closed loop system. The relative phase doesn't change the position, but it shifts the position of localization. So the microwave and radio frequency field create closed loop transition pathways. Because of this, the system becomes phase sensitive, and interference between different excitation paths determines the localization position. In this case, the atom localization shifted from one quadrant to the other quadrant if we change the position of the relative phase vector. So basically this is due to the microwave and radio frequency field. And
Himani, you've got 1 more minute.
okay,
Yeah.
sir. To
Okay.
conclude, okay. Now, to conclude in this work, we have studied high precision and atom localization in both 2D and 3D space using a 4-level delta inverter delta atomic system. Our results demonstrate that probe detuning, standing wave intensity, and relative phase vector plays a crucial role in improving localization precision. And these are the list of publications. Thank you for your attention. Thank you.
Thank you, Himani. So, questions from the audience. Please unmute yourself and ask the question. Any questions from the audience again?
Do check the chat room if there is any question in the chat room. Otherwise, you can thank that. This is the last one, and invite.
I got the question in chat box.
Not unable to.
Himani, can you check the chat once?
Okay, sir. Where is the chat box?
I mean, I want to ask one thing. What kind of localization you are seeing in these atoms? I mean, is it disorder driven or it is just correlation driven? Anderson type or Mott type or both?
So it is basically where we can find the atom in atomic vapor.
Atomic vapor.
Vapor, like in this case, we used the rubidium-87 atom.
Mm-hmm.
Yes. So we can find the atom localization in atomic vapor with the interaction of the different fields like laser field of rubidium and microwave and radio frequency field.
So, ma'am, in case of EIT, in this transparency, how this medium, like opaque medium to transparent in this case, and I will drop in comment box, but like something how light speed will velocity will speed will slow.
How can we observe EIT within mean? I think maybe
Rubidium vapor, you explain rubidium vapor in that mean if we are going to observe EIT like something these medium, so in such case, I think EIT medium in which light will be slow like something.
yes, by using in the dispersion phenomena we can slow down light.
So is it possible to slow down light maybe?
Yes, it is possible. It is already we can use the magnetic optical trapping technique to cool down light to cool down the atom and to store the light. So this is the technique to slow down the speed of light and to control it.
So, ma'am, if we want to make something like project for university, so rubidium vapor, you explain that. So, what should?
Actually, my work is purely theoretical.
Thank you.
Okay. So let's conclude this session, this talk. Thank you, Himani, for your nice talk. So you can unshare your screen now.
Okay, sir.
So let me go ahead with another speaker from Banaras Hindu University, which I'm also an alumni of, and he's Gaurav Shukla, and he will talk about the non-degenerate two-photon absorption. And I also know about this degenerate two-photon absorption, of course, but I do not know about the non-degenerate two-photon absorption. So let us listen from Gaurav Shukla about it. So Gaurav Shukla, are you ready? Gaurav?
Yes, sir.
Okay,
Sir,
go ahead.
does my slide visible?
Yeah, of course, your slide is visible and you are also audible. You can go ahead.
Okay. Yeah, thank you very much. Good evening, everyone. Myself Gaurav Shukla, and first of all, I would like to thank the organizer for organizing this wonderful seminar and giving me opportunity to present my work. So my topic is enhancing measurement precision of non-degenerate two-photon absorption. So yeah. So outline of my presentation is first I will introduce this two photon absorption phenomena and a little bit historical background of it, and then I will discuss this generalized error propagation formula, and then the results what we get in our calculation, and finally we conclude our result. So two photon absorption phenomena first predicted by Mary Goppard Mayer in her doctoral thesis in 1931, and the first experimental demonstration was conducted just after the invention of laser in European doped crystal. The first theoretists who predict this anti-bunching property in this TPA phenomena were the Naresh Chandra and Hari Prakash, and they evaluated the density operator for the interacting field up to the lowest order in time-dependent perturbation theory. So, single photon absorption, there is in two photon absorption there is a subselection rules. One of the parity change. Unlike single photon absorption, TPA allows transition between state of the same parity because of this product of two photon interaction results. And the other one is angular momentum conservation. So it demands total angular momentum change between the initial and final state must match the combined angular momentum of the two photons. So in our calculation, we consider this phenomena by using Markovian open quantum system dynamics, where this shows the evolution equation, where this rho is the density matrix and sorry, the density operator of the light field what we use on this material, and this L is the Lensbladian operator which shows the loss of two photons, and this gamma is the absorption coefficient which is related to the absorbance with this T times absorption coefficient, and where T is the time duration of propagation through the sample. So in my calculation, our objective to see the error in the measurement of this quantity epsilon. So due to since it is a nonlinear process, so due to weak light matter interaction, it possesses a very small cross section. We explore a possible improvement in the detection of this TPA signal on the output by using two mode squeezed state of light. For detection, we use some correlation functions like noise reduction factor, intensity correlation function, and normalized intensity correlation function. So a motive behind choosing these correlation functions are first, this noise correlation function, it showed like if this variance is less than this mean photon number, then it shows the quantum correlation between the output modes, and if it is greater or equal to this total mean photon number, the variance, so it shows the classical correlation between the output modes. And also in normalized intensity correlation function, this factor G11, if it is greater or equal to 1, then it shows classical correlation, and if it is less than 1, then it shows quantum correlation. Means this correlation function, we have a window where we can use this quantum correlation to improve this TPA signal detection. And one other important point to choose these observables is these correlation functions are frequently used in the experimental laboratories. In order to measure this error in the measurement, we use standard error propagation formula. But as we can see here in this noise reduction factor and in this normalized intensity correlation function, they are the already function of this photon number operator. So we cannot directly use this standard error propagation formula. So for this, we derived a
ওর এই কথার
generalized
জন্য
error
আমি লজ্জাতেও
propagation.
আজকাল কোনো তোর কথা কৌস্তব আঙ্কেল বা কেউ জিজ্ঞেস করলেন, কালকে আলোচনা করলাম বাধ্য হয়ে, সারাটা বছর আমাকে জিজ্ঞেস করেছে, আমি বলেছি টিলিপের খবর কি আছে, ওই আছে।
Please mute yourself.
ভয়ে আর কিছু বলিনি,
Mute
সেটা
yourself,
আমাকে
please.
জিজ্ঞেসই করতে না পারে। আমি নিজেকে এরকম করে একটা বন্ধ ইয়ের মধ্যে রেখে দিয়েছি যে বাবা
Yeah, thank you. Please go ahead, Gaurav.
Yes. So in generalized error propagation formula, so suppose we have an observable O which contains the information of the parameter of psi. So its Taylor expansion can be written in this form. Since epsilon is a very small quantity, so we neglect the higher order terms, and so we can write the variance in this form. And again, we consider this expectation value of this observable. So if it is a function of n variables, suppose x1, x2, and xn, so we can write it like this with this partial differential equation. So it can be written in terms of this partial derivative of x1, x2, and xn. And again, in terms of these variables x1 and x2, we can expand this this observable in this form. So in this case, this variance of the observable can be written in this matrix product, where A is the column matrix and this M is the covariance matrix, which shows the correlation between the these means variables, the x1 and x2. And combining equation 1 and 2, so we reached on this generalized error propagation formula. If we choose only one operator, like if O is suppose it has only one variable x1, so this covariance matrix reduces with this delta x1 square, and if we put this thing here, so it easily reduces in the standard error propagation formula. So using this standard error propagation formula and the observables, here I am listed the key findings, and these results are in terms of the mean photon number, what we consider on the incident on this sample. So and we listed all these findings here, where these shows the type of light, two mode lights, what we use on this TPS sample, like a two mode coherent state, which is the classical case, like we are shining two laser lights on this TPS sample, and this two mode squeezed vacuum case, where we just incident this squeezed vacuum modes on this sample, and the squeezed single seeded coherent case, it consider when we seed one of the port of this OPA, and in the double seeding we consider double seeding here. So and these are the correlation functions. So we found two interesting results here. In two mode squeezed vacuum case, as we can see in this noise reduction factor case, we cannot see any two photon absorption phenomena. In this case, this noise reduction factor gives us 1 upon eta, where eta is the this photon loss on the in this experimental setup. So and we can see, as we seed a single photon on a one-off seeding port, so it starts looking this two photon absorption phenomena. Means this noise reduction factor becomes like a switch on and off this TPA phenomena. And other is we get improvement in this in the sensitivity with the order of 0.5. For example, if we have we put 100 photons on this sample, if it is a simple coherent state, so in compared to coherent state, we get 10 times better result in this when we use this squeezed double seeded coherent state. So these plots shows this the improvement with squeezed light and coherent light, where dash line shows the coherent states, and these solid lines are squeezed light. And here we can see on improving this mean photon number, how this sensitivity can improve. And after that, we look in this lossy case also, where we consider different like a 10% loss and 30% loss. And we found that it is not necessary that we just squeeze light more and more and we get this improvement. But no, this is not the true. Here we found that with the photon number, we have some optimal squeezing where we get the better sensitivity case. For example, this panel shows for a single intensity case where this noise reduction factor we get to. And one more thing, this total mean photon number incident on the sample it consists the number of photons in the seeding and the number of photons due to this squeezing. So this axis shows the number of photons due to squeezing, and this axis shows the total mean photon number. So we can see in case of noise reduction factor in single seeding, we need for example, here it 547 means we need half number of photons due to squeezing and half number of photon due to this seeding. Similarly, in this G11 case, so in this case, we found that we need higher seeding and less squeezing. Like the mean photon number due to squeezing is here approximately 1 or less than 1. And in this normalized intensity correlation function, we found that this squeezing part plays a greater role. Like we need 998 photons with the squeezing and just the minimum number of photon with the seeding. And here this panel shows for the double seeded case. So overall, we found that in noise reduction factor and in normalized intensity correlation function, we need higher squeezing and less seeding. And in G11, like in intensity correlation function, we found that we need higher seeding and need less squeezing. So, and we also see that on improving the mean photon number, we can improve the sensitivity and can compensate this photon loss. Like we can see here in this G11 case, and in single seeding case, in double seeding case also. And one other important thing, what we found here for this normalized intensity correlation function, unlike in these cases, we can see there is a variation with the loss, but this normalized intensity correlation function shows maximum robustness against the loss. Yeah, it has a lower sensitivity, but it is a more robust than the noise reduction factor and this single intensity correlation function. So, so my work conclude that by using optimized squeezed state of light, we can minimize the estimation error of 2 photon absorption for different correlation functions. And this intensity correlation function shows there is an improvement of the scaling of 3.5 in compared to classical case. And we showed this normalized intensity correlation function is robust against experimental imperfections. And the feature of noise reduction factor is its ability to detect the level of single photon loss. Then hence it can give the experimental imperfection in the setup. So this finding, so this demonstrate the versatility and the potential of two-mode squeezed state in this transmission of enhanced sensitivity and precision in TPS signal detection. I would like to acknowledge my PhD supervisor, Professor Devendra Kumar Mishra, and my collaborators, Dr. Philip Slavin and Dr. Sairam Panohia. And for financial support, I would like to thanks IOE BHU. Thank you.
Thank you, Gaurav, for your nice talk. Any questions from the audience? Please ask your questions, unmute yourself and ask the question, or you can leave your question in the chat.
As I can see, one question is, what is the significance of power scaling 3.5 in photon flux? How would you experimentally
Verify.
verify the 3.5 scaling law? Actually, my work is pure theoretical. So how one can demonstrate in experiment? Sorry, I cannot comment anything on this.
Any comment, any suggestion for the experiment you can give?
From my side?
Okay.
Even if
Yeah,
somebody from
from
the
your
audience
side.
wants to comment, means like another experimentalist who works in the related area, you are
Yeah.
welcome to. And since now this was the last talk of the first session, and we have technically 10 minutes. We had a technical 10 minutes break. We can take a few questions, and even the questions from the previous speaker.
Yeah.
Sir, if we generally think that two photon observation, matlab something like two photons are coming and they observe like something a laser beam, like a lot of photons are coming and they will observe. It's I think it will black body radiation like something or that type. You explained that I think 1931 maybe. This experiment will start maybe in start of maybe I just want a imagination of this like something two photons are coming, they will observe, and what should we do like something in this case we will do some scattering.
This phenomena is first predicted by Mary Goppard Mayer in 1931, and its experimental demonstration was happened after 30 years in 1961, just after the invention of laser. So this two photon absorption is like material absorbing two photons simultaneously by following some selection rules. So sorry, I didn't understand your this, like what you would like to ask here.
Sir, actually, I just want one's imagination, like some you explained that two photons are coming, they are absorption, they observe, and we read, I think, black body radiation absorb light, they are photons. So in such case, what he think, what in 1931, what he think from where he's what need we will start to this experiment will start, and what's its benefit, and what's imagination we can create like something this we can't do experiment currently, but what's imagination.
What I can suggest, you can exchange your mobile number with Sufyan, and you can discuss it in detail on over phone or email if you want.
Okay, thank you, sir. You can share it. You can share your email
with you.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So Sufyan, you can exchange your phone number with Gaurav, and you can ask him later on in detail. Okay, Gaurav, so you can unshare your screen and this session ends. Thank you very much for your nice presentation.
Thank you.
And we would like to thank Gaurav as well as all the speakers who have spoken in this session, and also the session chair of this session, Dr. Gopal. And our next talk will start at 7:30, but there is a gap of 5 minutes, so we can generally discuss something. Means if anyone wants to share anything in general, announce anything, you can use this. Just like in the yesterday also, I told that if it was a real physical conference, we should have gone for a tea and then we would have a discussion. So now we can continue that discussion in the virtual mode, and start the next talk exactly at 7:30. So if you have any idea, you want to share anything or questions, comments on the things which has already been discussed, you can.
I want to ask question, but I am frightening of you.
Mukaram, your voice is a little low.
Sir, I want to ask question, but I am frightening like something hallucination from you.
Continue.
Sir, currently I ask question. Would you like to explain in your point of view?
I cannot follow you. Means what is my point of view about what?
Like two photon absorption. What? How can we imagine like something two photons are coming, they absorb? What's experimental? We can observe like something like Einstein is observing at Apple, so we can also in physics observe everything.
These are
So,
very routine nonlinear optical phenomena. Means, but to achieve all these things, you need a very strong light. So that's what the previous speaker was also telling. That means before discovery of the laser, this was not experimentally realized. You need a laser because laser does not diverge, and you can focus laser into very narrow area. So you can give. So you can think every nonlinear optical phenomena can be achieved in a strong electromagnetic field. So normally when you do polarization P, polarization is dipole moment per unit volume. It is proportional to electric field E, chi E. But when E is very high, then it become plus chi 2 square plus chi 3 cube and so on. But that requires a very powerful light where E is very strong, and these things can be if you think that you have an electron and you excite it half to the excited level, means not, but there is nothing to stand, so it should fall down. Or you are going up with a ladder and there is no step, then where you will stand? But if there are many particles which are pushing it, or many photons are there, then one can give the extra half needed and go upward. So that's the lucid visualization. But this phenomenon are very common in lab and not very unusual to see.
thank you, sir.
And as
Actually,
you told, that means from the 60s people are viewing it, so it's already about 60 years that one can observe this.
yeah, thank you, sir. Actually, I was just imagination of two phase like something when photons are coming, it's black body radiation. When it will completely absorb like something. When in another case, photons are coming like something metal surface or something another surface. So their electrons moving. They are so in. I just observing these two phase in such case photons case
Yeah, well,
which shows
these are routine nonlinear optical things, but just see any introductory discussion on nonlinear optics, and because we are speaking without a board or anything, so the visualization cannot be clear, means. But if you just see any introductory text on nonlinear optics, visualization will be relatively clearer. So the gap was short, and we are almost at the end of the gap, and let's slowly move to the. It's already 7:30, and so we move to the last session of the last day of the conference. But still, a lot of excitement is left. It's not like we are at the end of the meeting. And now I request Dr. Indrani Chakraborty, who is a faculty at JP Institute of Information Technology. She is our colleague, and she's by training particle physicist, but she works on the entanglement measures. She has interest, and she has interest in open quantum system. So there are many things which are related, and now people routinely see entanglement in particle physics. So over to Dr. Chakraborty for continuing this session and technically the last session of this 5-day meeting. So over to Dr. Chakraborty.
Yes, sir. Am I audible?
Yes.
Okay, thank you, sir, for the nice introduction. So this is the last session of this conference, and it will be about quantum information. There will be back-to-back 5 talks. So the first talk will be by Dr. Kathakali Mandal from Tamkang University, Taiwan. Kathakali, are you there?
Yes, am I audible?
Yes, you are audible. So she will be talking on Gaussian boson sampling, theory and mathematical framework. Kathakali, you can share your screen and start talking. You have 15 plus 5 minutes to complete your talk.
I can't share.
Wait, there is an arrow. There is an arrow. Click on the arrow. Somewhere bottom of in the middle of your screen, there will be a.
Oh, yes.
Yeah.
My screen is visible
Your
now.
screen is
Yes,
visible, but
yes.
not full screen. Let's make it full screen.
Is
Fine.
it now?
Yes,
Perfect.
yes.
Okay. Okay, good evening, everybody. I am Kathakali Mandal from Tamkang University, and thank you, organizer, for giving me this opportunity. It's always very nice to join an event organized by own department. So, yeah. So recently, I am start working in continuous variable quantum computing, and then find it the Gaussian boson sampling is very important. It can produce non-Gaussian resource which can help scaling quantum computing. So I believe that this little detailed discussion will help the young researcher in this field. So before directly going to Gaussian boson sampling, we should understand the boson sampling, and before boson sampling, we should understand the classical picture of it. So it is a Galton board. If we put balls from here, it will go left or right from peaks. So, and in the end, we will get a probability distribution, or if we run the experiments many times, we'll get many distributions. So we call it sample. So we can compare it with a quantum picture. So in quantum picture, the balls are photons, non-distinguishable. I produced this picture from ChatGPT, and that gives it different color. It should be the same color. So anyway, so the pegs we compared it with beam splitter or phase shifter. So if we put photons through this interferometer, and we'll get probability distribution of photons, and detect photons and we'll get distribution. So here, but the difference from classical picture is this is very complicated, and we'll get there's lots of possibilities, so which cannot be done by classical computer. So here it's come quantum advantage. So here is the boson sampling. So boson sampling's model or scheme first proposed by Aronson and Arkhipov. So their schemes is like if we n photons are injected in a interferometer, and we'll get a particular distribution here, then the probability of getting a particular distribution n bar will be this. So here TS is the submatrix of the matrix T. So how could we calculate TS? TS will be, if we put here, so let's take the 3 photons are going from first 3 input, and we are getting output here in 3. So these 3 are the columns, and this row are the output. Then this matrix, this will be the TS. So, and by using TX, we can get the probability. Now I count Gaussian boson sampling. So we need Gaussian boson samplings because we can't, getting many photons, single photons, is experimentally very hard. So, but getting Gaussian state experimentally is relatively easy. So squeeze state. So Hamilton and all proposed the Gaussian boson sampling scheme. So instead of single photon Fock state, they replace its Gaussian state, and non-classically induced by linear optical network like beam splitter and phase shifter. So here the Gaussian, any M-mode Gaussian state can be fully characterized by 2m cross 2m covariant matrix. I know that, and displacement of vector. So from covariant matrix sigma, we can get easily the Q function, and from there, using the P function, we can get the probability distribution here. And here is, so for a particular probability distribution, the probability of getting particular probability distribution is this. So in the boson sampling, where it was per frame of TS, and it's a Hoffmannian of AS. Now, how could we calculate the AS? AS also a submatrix of A, and the state matrix, and it's again we AS construct like that. The difference is in here, the AS not depending on the inputs, is only depending on the output distribution. So Gaussian boson sampling with squeeze state. So if we pass single mode many squeeze states for an interferometer, and here is the detection, and this is the model, and here the squeeze state can be written like that. For M mode, this operator, this function is this. And so after interferometer, the covariant matrix would be this, and this formula we can get the probability of a particular distribution by this formula. So now recently in this paper, they show that they show the scheme a multimode non-Gaussian state generator, where they propose a control parameters which can by controlling this, we can control the non-Gaussian state. This setup shows that this setup also refer as a Gaussian boson sampling. Here is the L plus K mode Gaussian state, and if we measured here the first K mode, then we'll get here L mode, non-Gaussian L mode. Also, this is also a scheme to generate GKB state, where we put the 4 Gaussian state. I recently calculate for very small, simple model where n is 2, and changing control parameter, I calculate the Wigner function of the non-Gaussian state, which produce here signal. In control, we measured the others not actually. So then I can get that if you increase the yeah, S0 control, then you get, this is the cat state, actually cat. So here, so the Gaussian boson sampling, you can see that Gaussian boson sampling can use to generate non-Gaussian resource like also GKP state, which is very important to scaling quantum computing. So yeah, this is my presentation, and we are now trying to design a model where we can get non-classical, non-Gaussian resource from this kind of setup. Thank you.
Thank you, Kathakali, for the nice talk and also finishing on time. Is there any question from the audience? If you have any question, please unmute yourself and ask the question. You can also write it in the chat box.
Hello, am I audible? I have one question.
Yes.
Ma'am, my question is you told this method is particularly used to create non-Gaussian structures. We already
Yes.
have multiple methods. For example, if we add, for example, photon addition, unequal photon addition can also create non-Gaussian structure.
Yes,
So how
Sorry,
is this unique? And second, ma'am, can you please elaborate little on Hafnium? What is that?
Okay, Hafnium is the I add, sorry, should I hide it, share it again? Okay, I put a short note for Hafnium. Hafnium is if I get elements pair here, suppose matrix here is 1, 2, 3, 4, and the 1, 1, 2, 3, 4, like that. The Hafnium will be A1, 2 into A3, 4, and A1, 3 into A2, 4, and A1, 4 into A2, 3. And also this is the prim A. Prim A is this. Yeah, I think you understand.
Yes, ma'am. But ma'am, why? Maybe I can look into it later. But my question is, ma'am, why this particular method is unique? Because already, already we have multiple methods to create Gaussian states.
I think normal photon subtraction here also it's happened in photon subtraction actually, and for many mode non-Gaussian state generator, I think it will be this will be helpful. Many mode non-classical, non-classical, sorry, non-Gaussian resource.
All right, ma'am. Thank
And
you.
we can control it. Actually, we can control it actually in our way by detection is detecting parameter changing and all this S0 and L0.
All right, ma'am. Thank you.
There is one question in the chat box. Can you please see the chat box?
Okay. Why is the Hafnium considered classically hard to compute? Yeah, actually, when for interferometer photon will pass, you will get lots of option, and there's lots of variety. I mean, it's many probabilities. So particular, suppose probability distribution particular n dash, so we'll get many. So it because of the number that will be, I think, but it's difficult. And yeah, because of the interferometer, it is, superposition of this either here and here. So it's obviously it will be difficult simulating in classical computer by classical computer.
Any other question? If not, Let's thank the speaker again. Kathakali, you can now unshare your screen.
Okay, how
Thank you
to
again.
do that? Okay, I think it's unshare already.
It's done. It's done.
Yes, it's done.
Okay, thank you.
Our next speaker is Dr. Sandhya Pundhir from NIT Delhi. The topic of the talk is Quantum Machine Learning as the Brain of the Quantum Internet, Advances, Applications, and the Path to Fault-Tolerant Security. Dr. Sandhya, you can now share your screen using the share screen button below.
Mhm.
Yes, it's visible.
It's fine, ma'am.
Yes.
Perfect. Please continue. Please start talking.
Good evening, everyone. And thank you to the organizers. So let's start with the topic, the quantum machine learning as the brain of the quantum internet, the advances and the applications and the fault tolerant. And I will be covering this in the various categories, or you can say the content will be under like motivation, what is the internet concept, the architecture, the various challenges it faces, and the QML is the quantum internet's brain, and some quantum advances and applications and the various concepts. So starting with the quantum bit versus the classical bit. This is the main core protocol or the concept that used in the quantum internet. It is showing you the 2 bits, the classical channel, as well as the dotted one, that is the quantum channel where the quantum states are being transferred, and thus the 2-bit classical channel act as the instruction. So this is a hybrid kind of, you can say, to transfer the information in the quantum internet. So what are the motivations? Like future global network requires the ultra secure communication, and this internet enables entanglement based networking and need the intelligence control for routing, noise mitigation, and security. And this QML provides the adaptive optimization dynamic. And as we all know that classical AI has its own limitations, so we do know reach to the QMLs. So like Web 1.0 was a static web, Web 2.0 the social web, Web 3.0 the decentralized, and Web 4.0 the intelligent and the symbiotic web. The future network will transmit the quantum state, not just the data. That's the base of the quantum internet. So what is it? It is a network that uses quantum signals instead of the classical bit, and it transmits the quantum state between the 2 nodes. So the key features, the key protocols, the processes that are being used in the quantum internet is the quantum entanglement distribution. This is basically how the state is being transferred from one node to the another. These are the various methods. Distribution is used, and process is called the teleportation. Then the distributed quantum computing is there, how the various quantum nodes connect and show it like one single supercomputer. The global network distributing quantum states, an unbreakable, unhackable security mechanism, that is quantum key distribution, is used here. So this is how a quantum network look like. And the physicists have created a network that link the 3 quantum devices using the phenomena of entanglement, and each device holds 1 qubit of the quantum information that can be entangled with the other 2. Like in lab 1 there are the 2 nodes, in lab 2 has another node, how they are entangling or transferring the data with the other. So architecture has the topmost application layer that used for secure communication, then AI control layer, the quantum network layer, the physical layer, and the various components used will be the quantum nodes, quantum repeaters, entanglement links, and the quantum memory system. So why we need the quantum repeaters? Because of the chances of the photon loss. So the challenges that are in this system, the decoherence and the noise, that the photon may lose its data, the limited entanglement distance, the entanglement cannot be achieved at the longer distances, the routing complexity that arise in the system, the security vulnerabilities, and the scalability, because need of the million of stable qubit will be required, and the hybrid control that to work efficiently with the system. So we come to the advancement, that is quantum machine learning. This is like an intersection of your quantum computing in the AI, and it work in the quantum Hilbert space, a mathematical space where quantum state can be calculated. And this is the quantum classical optimization based working. And this QML acts like the adaptive brain that learn from the noise. It optimizes the routing and predicts the failure in the system. And it do leverage and uses the quantum properties to improve the learning performance of the system. So why we go for QML for the internet? Because this machine learning produces a more real and the probabilistic data, learns the best path and allocation strategy, adapt to the network circumstances, learns the noise pattern, adopt noise mitigation, predict demand and congestion. It is self-optimizing network, scalable and more secure. So it can learn dynamically at the runtime, adopt with the various machine learning capabilities into the quantum machine learning. So like we can show a quantum internet like it's the mathematical way, where V is a set of quantum nodes, E is the quantum channels, and EI is that is quantum channel between the nodes I and the J. So applying the variational quantum algorithm, the internet behaves like a feedback system. So this is the quantum pipeline that is applied. There is some other work also that I have done, but that is under process, or you can say under consideration. That's why not included here. So we have some input, the classical input, then that will be transformed to the quantum state, then encoded with the classical data into quantum state. Encoding will be done, and then the quantum circuit, the parameterized transmission, and then the measurement of the expected value. A loss function is applied, and the training update rule will be there until a satisfied expected value is not achieved. And it will be different for the different kind of applications. So this quantum internet go for the optimized result over quantum state, and these optimizations use the high dimensional value and quantum natives, and this QML provides the efficient representations, trainable optimization and adaptive controls. So what are the difference or comparisons? We can go for the classical ML and the fault tolerant QML. That classical uses billions of the GPU. In fault tolerant QML, we can go with the thousands of the logical qubits. The feature space require polynomial time. Here, exponential Hilbert, error resilience, robust to the noise. It requires QAC overheads. Speed up is linear and quadratic for the QML. So some contributions and the benefit in routing and scheduling. It's learn optimal entanglement path and give the fidelity improvements and error reductions, predict channel noise, and resource allocation, optimize the qubit memories in the real time, and it has its own benefits. So why we call QML as the brain? Because like all the functionality of brain, it senses means process the quantum telemetry, takes the remote data, learns. It may use quantum kernel, it may use neural network and other models to learn from the complex noise patterns, act in the real time, do the optimization, do the routing, error correction, resource allocation. And loop can be there, like you have a quantum data, then classical training and quantum deployment. So the various brain functions similarly being adopted here or done by the ML in the quantum internet. So these are the various applications that are there: secure communication, quantum computing, sensing the network, cloud infrastructure, adaptive routing, predictive maintenance, QAD, and in the drug discovery, finance optimizations, etc. So top 8 quantum applications are these. And without QML and with QML, like static routing was there, now self-learning, no adaptive error correction, here the dynamic entanglement optimization, poor scalability, and fault-tolerant intelligence. So fault-tolerant quantum computing basics, because it can provide the quantum error corrections. It has logical qubits, it has surface codes, logical qubits encode, one logical into thousands of physical bytecodes, and some threshold theorems can be applied there to go for the fault tolerance. And the future of the quantum internet, global satellite quantum communication, AI-driven network, autonomous quantum infrastructure is there. So roadmap to deployment, like in these years, these kind of things are being working there. And these are various global initiatives that being done. And conclusion, QML intelligence, secure brain transforming, and quantum internet from vision to reality. It's not just a theoretical concept, it's being developed by countries and being currently used. That's all. Thank you.
Thank you, Dr. Sandhya, for the nice talk. If you have any questions, please ask the question. I think there is a question in the chat box.
Okay, ma'am.
May I ask a question, Dr. Sandhya? Hello.
I'm trying to see
The question is, I can read it.
Uh-huh.
How to
Yes.
reduce photon loss and how to reduce data loss long distance experimentally.
Ma'am, we can apply the quantum error corrections method to overcome all those. And there are various other methods that we can employ. Or that can be specific to the applications.
Okay. Is there any other question?
Yeah. May I ask a question, Dr.
Yes,
Sandhya?
sure. Proceed.
Yeah. So the question is, when you are trying to use quantum machine learning and also for this quantum internet thing, while the decoherence problem is already there. So when you are trying to use it for the optimization purpose or learning purposes, the scalability between the probe and the target itself are of the same nature of complexities. So how you try to overcome those things? Because as a theory, in practical sense, this is one of the limiting factor, and there are many others.
Sir, like
when you are putting this proposal, what are the possible?
So like we can go for the variational quantum algorithms. We can go for the inherent noise resilient methods. Those
No,
do
but I am
cancel.
talking about when you are, the point is if I understand it correctly, you are claiming that using quantum states or using quantum resources, you will be able to more efficiently read out the errors, quantum error, like
Right,
decoherence, as well as similarly the correlations. And
Right.
for that, your quantum state must be there in the coherent state. Otherwise, how you will do it?
Sir, initially
So
it is a tough task to achieve.
The time scale of the coherence is both intact. So how you will use if the probe and the target both are of facing same level of errors, or just to be precise, decoherence, then how we will do that?
So I understand, because you're saying until we are not achieved a stable system, then how we can apply this, right, sir?
Yeah, and also there should be a difference in the time scale. So you can't do it with so the probe state must have relatively longer coherence time than the target state. Otherwise, you can't do it.
Definitely, sir.
Decoherent. Yeah. So
Sir, actually, there is the limitation of the hardware, but we are working because the hardware work is still so much in the process only.
Yeah. So my question was how you will scale it differently. It's not only about achieving the coherence; it's about achieving the different levels of coherence. So is there any outcomes from yours or in general from the community who is working exactly on this problem?
So actually, to go with the noise resilience and shallow circuits that work instantly at movement with that data only, or that interaction only, that we can go for that.
Okay. Thank you.
Okay.
There is another question in the chat box. Can you see it? I think it is a long question, so I can read it for you. It
Okay.
is a question from Manish Tiwari.
Mhm.
Hello, ma'am. I am a third year engineering student with an AI background and strong interest in quantum computing. From your slides, QML is proposed for routing and error adaptation. Could you share how the AI control layer actually interfaces with the quantum network layer to enable that real-time optimization?
Actually, currently, I have achieved it with mathematics only. So at physical level, I can't say. Only at mathematical, you can say, or the concept level only, this work is being done from my side.
Okay. Is there any other question? If not, thank you, Dr. Sandhya, for the very nice and insightful and also informative talk. You may unshare your screen now.
Right.
We can now move on to the next talk by Debanjan Roy from Bose Institute. The title of the talk is Quantum State Exclusion with Many Copies. Debanjan, you can share your screen. Please go to the full screen mode.
Am I audible?
Yes, you are.
Okay, so
You can start. Yes.
thank you, ma'am.
You are audible, but your voice is low.
Okay, let me check. Well, I'll talk louder. Okay, so first of all, I would like to thank the organizers for providing me with the opportunity to present our work. Today, I'm here to talk about quantum state exclusion with many copies. This work has been done in collaboration with Tathagat Gupta, Pratik Ghoshal, Samrat Sen, and Professor Shantanu Bandyopadhyay. So this work is available on arXiv. The arXiv posting is given over here. So if you're interested, you can check it out. I have divided this presentation into 3 parts. First of all, I would like to explain the state exclusion, and then I would move on to motivating the many copy activation and present some of our main results. And finally, I will leave you with a few open questions and conclude the talk. So, in contrast to classical mechanics, quantum mechanics forbids the distinguishability of non-orthogonal states, perfect distinguishability, I should say, of non-orthogonal states. Only the mutually orthogonal states are perfectly distinguishable, and this weird phenomena that has no classical analog underlies a key quantum phenomena that is called the no cloning theorem, which forbids the replication of unknown quantum states. Now, far from being a limitation, this actually serves as a resource because it enhances or ensures, I should say, the security of the quantum cryptographic protocols by making eavesdropping intrinsically detectable. Now, this quantum state discrimination is widely studied, and but for non-orthogonal states, as I said earlier, the perfect discrimination is not possible. So for the impossibility of perfect discrimination of non-orthogonal states, we consider some other variants. Suppose we can, in case of discrimination, we can consider the including finite error in the measurements outcomes, or use the inconclusive outcome method. One of the other ways to tackle this is the quantum state exclusion, where we do not ask the question which state was prepared by the referee. Where in case of non-orthogonal state, this is particularly useful because we can extract some reliable information out of imperfect reliable information out of the state, and we are interested in answering the question that which state was not prepared. Now, in this talk, the key question I'm addressing is, or we have done, the work we have done is that if given a single copy, the state exclusion or anti-distinguishability, suppose it's not possible because not all set of states admit state exclusion. So if we have finitely many copies, if the referee provides the player finitely many copies of the system, then is it possible to perfectly anti-distinguish the set of states? And if we are understanding this phenomena, actually opens up new facets of quantum mechanics, which finds relevance in quantum certification, one-shot communication, and foundational studies of non-classicality. This is a mathematical framework. Suppose I have a set of states S, and given a P of M, we can tell that the probability of obtaining outcome I given the state rho I is given by the Born rule, and the set of states performs state exclusion. That means there exists P of M elements labeled M1, M2 up to Mk that admits state exclusion if the right hand side equals to 0 for all I, for all states in the set. And as I said, if we get the outcome I, then we can conclusively tell that with certainty that the rho I, set rho I was not prepared. So, the state exclusion has two variants. One is strong state exclusion and one is weak state exclusion. The graphical depiction of the two variants have been provided in the slide. The rough difference in strong state exclusion and weak state exclusion is that in strong state exclusion, all the measurement outcomes finds relevance. So no measurement outcome is redundant. And that is provided by the second condition, that no measurement element is redundant, no measurement outcome is redundant. That is given by this sum over trace rho I mj greater than equals to 0 for all j. This is a strong notion. If both the conditions are satisfied, then we tell this is a strong notion of anti-distinguishability or strong state exclusion. So let's illustrate this with a couple of examples. Let's step through the first example. The set of states K0 plus K1 and K1 plus K2 and K2 plus K0. If we perform projective measurements with the K0, K1 and K2 basis, then if we get outcome 0, then we can say that K1 plus K2 state is excluded. If we get outcome 1, we can say K2 plus K0 state is excluded. And if we get outcome 3, we can outcome 2, then we can K0 plus K1 state is excluded. And if we get outcome 2, then we can say K0 plus K1 state is excluded. These are unnormalized state. And the next one is a very famous example of trine states, which is anti-distinguishable and in a single copy. But many set of states do not allow exclusion. Exclusion is not achieved in all the set of states. And this has been illustrated by a couple of examples. The K0, K plus, and K1. That example is will come in the later on in the lecture, in the talk. So let's move on. This is the schematic diagram of what I was telling earlier. There is a referee, there is a player, and the referee draws, conceptually, the referee draws one of the states out of the set, and the set is known to the player as well. The referee draws one of the state out of according to some probability distribution and hands it to the player, and the referee asks the player, which state I have not given you, have I not given you? And if the player can answer this question perfectly in every run, then we can say the set of the states is anti-distinguishable. Here we can say the probability of getting the outcome I is given by the Bond rule again, and if the bond is this expression equals to 0 for every I, then we can say that this is the anti-distinguishable and this is the anti-distinguishable condition. This is as I said, this is famous prime state example, and the states are the excluded. The measurement elements are expressions are given, and for qubit case, this is a qubit case. So for qubit case, the states on the block sphere, qubits on the block sphere, the convex hull of the block sphere, if that contains identity by 2, then we can say that the set of qubit states are anti-distinguishable. Now moving on, as I said, single copy failure is possible, and please recall the set of states K0, K plus, and K1 that does not admit state exclusion. And if we have, so we are asking that if we have multi-copy, then can we achieve state exclusion? So suppose we have infinite copies. Let's go to the other extreme. So if we have access to infinite copies, if the player has access to infinite copies of the state, then tomography can be done, and we can reconstruct the state. So this won't be very interesting in this case. So finite copies suffice. So can we achieve this as finite number of copies? So in this case, K0, K plus, and K1, this set, if we have 2 copies of the state, then with joint measurement, we can achieve anti-distinguishability. So that actually motivates our work on multi-copy anti-distinguishability, activation of anti-distinguishability when you have access to multiple copies. So this is again what I have said that has been described mathematically. And to recall, the key question was, if we increase the number of copies, does the state exclusion become possible, which was impossible earlier given a single copy? So that was answered by our first theorem. Suppose we can say that if we have 2 copies of the set S, then we are able to achieve anti-distinguishability or state exclusion. So increasing the number of copies helps, but does there exist some set of states where if we increase the number of copies, that might not be able to achieve anti-distinguishability? Is that the case? So our theorem answers that in the negative, that every set of 3 or more pure states that is not anti-distinguishable in the single copy becomes anti-distinguishable when you have finite number of copies. So here we have in the paper we have derived a general bound, which is a function, a ceiling function of the maximal pairwise overlap, and a function of the number of states in the set. So state cardinality and the maximal possible overlap between the states. So multi-copy access definitely increases exclusion power, and all sets of pure states. I mean, we can ask why not set of 2 pure states? Because in set of 2 pure states, the concept of distinguishability and undistinguishability are equivalent. So that is not very interesting to this trivial, right? So, and the required number of copies actually it depends on the set of states. But this bound, general upper bound, we have found that is not tight, but we will find later on that instead of very special cases, we have found the exact number of copies required, and that the multi-copy scenario has. Sorry, is there a question? Sorry, so I'll move on. So the multi-copy scenario actually motivated us to this definition that if we have a natural number positive integer n, that a set of quantum states is n copy anti-distinguishable if it is only anti-distinguishable with n copies of states with access to n copies. But if we have n prime number of copies which is less than n, that in that case anti-distinguishable only, so state exclusion only possible. So as I said, that in that n copy anti-distribution leads us to the following theorem, that in very special cases of quantum states, set of quantum states, where we have equal and real inner product, that is gamma is represented with gamma. So in case of all the inner products are equal and real, so in that case we can calculate the exact number of copies required for anti-distinguishability of the quantum states, and which is a function of the state cardinality and the inner product gamma and cardinality k. So however, as I said, the number of copies required depends on the state set. So does there exist, we can ask natural question, we can ask that does there exist a number, natural number n, where we can say that with at most n number of copies, all the set of states get anti-distinguishable, or anti-distinguishability can be, or state exclusion can be achieved with all the for all the set of states with a upper bound of n number of states. So this question is answered in the negative by our theorem, this theorem. So there is no universal finite bound on the number of copies. So the number of copies required can become arbitrarily large. Okay, it can increase, it will be finite, but it will be arbitrarily large. And the next theorem actually goes along with the previous theorem, that we can have a positive integer n, but there can exist pure states. We are only dealing with pure states that are n plus 1 copy anti-distinguishable. The previous theorem was that there exists set of pure states for every natural number positive integer n that are not n copy anti-distinguishable. So the number of copies can become arbitrarily large. So, and however, we can characterize, as we have characterized the real and equal inner product case, we can find the case of 3 pure states where we have the equal overlaps, and we call this squared pairwise overlap, which is given by x, and which is the modular squared of the inner product, and the state is n copy anti-distinguishable if x lies within the range given on the slide. So from the range, from the value of x, from the range we can determine the number of copies required, the necessary and sufficient number of copies required for the set of 3 pure states to admit state exclusion. And let's illustrate this with an example. So we have a set of 3 pure states but qubit states here, which are parameterized by the parameter theta. So, and they have equal pairwise overlaps, squared pairwise overlap given by cos square theta over 2. In this case, we can find the exact number of the necessary and sufficient number of copies required for the states to admit state exclusion, quantum state exclusion. So let's look at the plot. As you can see from the chart, that the number of copies required for the set of states to admit state exclusion has been plotted as a function of theta, the parameter, and as theta approaches 0, we can see that the cos squared theta by 2 will approach 1, right? So theta decreases and cos squared theta with the squared overlap, pairwise squared overlap increases. And from there, as you can see from the graph, that as theta reduces and approaches 0, the number of copies becomes arbitrarily large. And this is also a result that we can determine exactly how much copies are required and how that is reflect the dependence of the parameter theta in the family of set of 3 qubit states is reflected in the number of copies as a function of the parameter theta. And
Debanjan, sorry to interrupt you. You have 1 more minute.
Okay, I'll conclude. So this is the open question. So the optimal number of copies remains an open question, and we have not considered any constraint measurement. We haven't imposed any restriction on the measurements. So that also is an interesting direction study. And we can also extend to mixed states, because in this case, in this work, we have only considered pure states. And this is the key take-home messages. So I won't go through it once more, because we have already discussed this for paucity of time. And so that brings us to the end of my presentation. And I'll be happy to answer any questions you may have. Thank you very much.
Thank you, Debanjan, for this detailed talk. Is there any question? If there is any question, please unmute yourself and ask. Okay, there is one question in the chat box. Debanjan, can you read it?
Yes, just give me a second.
Sure.
Is the screen unshared now?
No. No.
Stop sharing, and I will read the question. So, what is undistinguishability and how is different from distinguishability? So, as I said, the question of undistinguishability actually reverses the question of distinguishability of quantum states. Because in distinguishability, we ask the player, that the referee asks the player that which state I have given you. So if you can tell with certainty which state, or identify with certainty which state the referee has given the player, if the player can answer the question perfectly for every time, then the set of states are distinguishable. And the distinguishability condition is that the set of states are distinguishable if and only if in case of single system, if and only if the set of states are mutually orthogonal. But in anti-distinguishability, we flip the question on its head and we say that which state have I not given you? Suppose you can tell that you have not given me psi 2, and if I have given you psi 1, then you will win the game, and that will be this. And if you can win every time, then the set of states will be anti-distinguishable. So have I answered your question? It's a different kind of phrasing, but foundationally and operationally it's very important and very distinct. But it's a different kind of phrasing, you can say, but different phenomena. Okay, and is there any more question?
Any more questions? Thank you, Debanjan, for the detailed talk.
Thank you, ma'am.
So our next speaker is Pritam Roy from SN Bose National Center for Basic Sciences. He will be talking on robust certification of quantum instruments through a sequential communication game. Pritam, are you there?
Yes, ma'am.
Okay, you can share your screen.
Okay. Is my screen visible to all?
Yes, it is. Please, okay, yes, it is visible. Please go to the full screen mode. Yes, perfect.
Okay. Hello, everyone. I am Pritam Roy from SN Bose National Center for Basic Science, Kolkata. First of all, I would like to thank the organizer for giving me opportunity to present my work here. Today, I will discuss our recent work, robust certification of quantum instrument through a sequential communication game. This work is recently published in Physical Review A, and these are my collaborators. Shubhankar Bera and Shiladit Tumal is my senior, and Professor Archana Majumdar is my supervisor. So this is a brief outline of today's talk. First, I try to motivate why we need certification of quantum devices, and particularly the quantum instrument, and then I will discuss our protocol, and then the quantum advantage and robust self-testing, and then the generalization to the higher dimension and summary and future direction. Okay, so why we need certification? All the quantum technologies like quantum key distribution, quantum computing, quantum random number generator, all depends on black box devices. Why these are black box devices? Because we buy from a supplier, and that supplier may supply a malicious device to harm our protocols, right? So we should always not trust the supplier, and we should always certify our measurement and preparation devices. So based on the trust issue, that certifications are described in three ways, like device dependent, where we trust the full device and we use this type of things for tomography. Like if we try to certify state is entangled or not using the witness based approach or some moment based detection approach, then this turns to be a device dependent protocol. And the device independent is quite famous than the other two, because we all know that device independent quantum key distribution, device independent random number generation. This is basically this like this figure. There's all the source and measurement device all are untrusted. So we only trust the classical input and classical output. So based on these statistics, we try to certify our state is entangled or not. And other one is a semi-device independent. Why this is semi-device independent? Because in this, the preparation and measurement device is not trusted, but the dimension of the system is trusted. Our study, it falls in this category, this semi-device independent study. So as I said in the previous slide, that in this black box setup, we should always trust only the input and output statistics. And based on that, there are different standard self-testing that based on the Bell CHSH violation, we can say a state is singlet or not, up to some local isometry. And also based on some protocol named as quantum random access protocols maximum success, we can say our measurement is a Pauli measurement or not. Okay, but the main limitation of standard self-testing is it only limited to the up to the measurement. But in measurement postulate, we know that we always get a classical outcome as well as a post-measurement quantum state. So to incorporate that post-measurement quantum state, we need to go to the quantum instrument, because quantum instrument captures both the classical outcome as well as the post-measurement state. You can see from this figure that this is our initial quantum state, and we put it in a quantum instrument, we get a classical output as well as a updated state. So how we mathematically describe a quantum instrument? A quantum instrument is a set of CPTP map. Okay, and if we try to write down this CPTP map in terms of our known Krauss operator representation, then this looks like this. So instrument is basically gives us a classical outcome as well as the state update. So now if we move to the certification of quantum instrument, specifically in our work and in the first work, people try to certify the unsharp measurement based instrument. So first work is done by in 2019. Mohan, Tavakoli and Brunner, they first show that quantum instrument could be certified in a semi-device independent manner. What is their scenario? They consider again a quantum random access code where there are two receivers and they independently plays with Alice and get the success probability trade-off, and from that they try to certify quantum instrument. But there is some problem. In their protocol, this is very much noise sensitive. So under realistic situation, we should make our protocol more robust. So in our task, our goal is to improve this robustness. We design a constrained communication game with a collaborative structure. Okay. So before going into our protocol's details, first let us discuss the basic random access code. In the basic random access code, this is an information task where Alice has a two-digit bit string, this 00011011, but she can send only one bit in a given run of experiment. And Bob's task is to guess either x0 or x1 with equal probability. Bob get a input y and Bob need to guess the yth bit of x, right? So under this one bit constraint, the maximum classical success probability is achieved only 0.75. This is the best success probability. How they can achieve? Alice can share any of these two bits, x0 or x1. Then whenever Bob is asked the ith bit, then they get, if Alice send m equals x0, then Bob guesses x0 correctly with probability 1. But if that is x1, then he must to guess randomly with 0.5. Then the average success probability, as two question coming with equal probability, then we have to take the average, we get 0.75. So this is basic classical random access code, but there is a quantum advantage. Instead of a bit, if we use a qubit, and we suitably choose an incompatible measurement, you can see from this figure, if we suitably encode this 00011011 message like this type of antipodal points and perform a incompatible measurement, we always get a success 0.8535 in ideal condition. So let's come to our protocol. In this protocol, you can see this is we need to incorporate the quantum instrument part. You can see in the middle part that Bob has a classical outcome as well as a post-measurement quantum state. So Bob's instrument, Bob's device is in this case the quantum instrument, and Alice's device is a preparation device, and Charlie's device is a measurement device. So in this game, we analyze like that. Bob need to guess. Bob randomly guess 0 or 1th bit of Alice's message, and this y can be chosen from 0 and 1 randomly, but Charlie guesses the remaining bit. That means if Bob guesses x0, then Charlie's task is to guess x1. Okay, but there is a restriction. Bob passes the state to Charlie with no information about his output revealed. Bob cannot reveal any information about his output. Okay, so you can see that Bob acts as a quantum instrument and balancing the information gain with the preservation for Charlie. So the mathematical definitions here, the average success probability of Bob is given by this thing. This is Bob's output B. Bob always gets success when B is equals to X, Y. And Charlie is always gets success when C is equals to X, Y bar. Okay, and this is the post-measurement state, updated state given to Charlie. And in this case, if we calculate the classical success, it follows standard RAC protocol, half into 1 plus 1 by D. Here D is the dimension of the classical system. And in Charlie's case, there is no additional advantage, so Charlie need to guess randomly, 1 by D. And these are quantum success probability, we need to optimize this. Okay. So first simplify the protocol, choose D equals 2. Then we need to solve this optimization problem. You can see for a given value of success of Alice and Bob, let's say beta, we can always optimize Alice and Charlie's success given this constraint that the state should be a valid qubit state, and all the properties the state should follow. And their main constraint is that this one, 1 by 4 sum over x rho tilde xy equals identity by 2. So this means the no information leakage from Bob to Charlie. This is the main constraint here. Okay, if we solve that problem, we get this type of states and measurement of Alice, Bob, and Charlie. And from that, we can get the optimal success probability PAB and PAC. Both are function of some eta. Eta is a unsharp parameter of Bob's measurement. Okay, so by varying eta, we can see that this, if we plot PAB given PAC, then this red line is the quantum optimal solution. And by varying eta, we can move in this curve. Okay, when Bob get maximum success, Charlie get lower success. When Charlie get maximum success, Bob get lower success. Okay, so what our self-testing result for an optimal pair of average success probability, let's say for beta and PAC for a given value of beta, we self-test the following physical quantities. Alice's state preparations are like this. These are again the antipodal points similar to the RAC. But Bob's measurement is not the sharp measurement, and this is unsharp one. That's why I write a lower arrow than the sigma z. You can see that if we put eta equals 1, then we get a sharp measurement for Bob. And if we put eta equals 0, that is a trivial measurement. So eta is a controlling parameter of sharpness of Bob's measurement. And Charlie's measurement is again a rank 1 projective measurement of up to some local unitary sigma x and sigma z. And if we solve some mathematical equation, then we get some lower bound and upper bound of eta. You can see that this lower bound and upper bound depends on probabilities. The lower bound depends on Alice and Bob's success probability, and the upper bound depends on Alice and Charlie's success probability. So in experiment, if we calculate PAB and PAC, then we can always estimate the upper and lower bound of eta. So our main goal is here to certify this eta parameter. So in ideal case, these results are very good and it complements the Tavakoli's result. And but in robust for under noise, if we choose a noisy preparation like a white noise and a noisy measurement device also for different values of noise parameter, if we make a table and calculate PAB, PAC, and PAC star is the success probability of Alice and Charlie of Tavakoli's paper. And if we try to estimate the gap between lower bound and upper bound of eta, then we get a significant improvement than the previous one. This delta star is upper bound and lower bound gap from Tavakoli's result, and this delta is our result. We can see almost half of the value. So smaller the gap means better certification. Okay. Then we generalize that optimization problem using seesaw optimization and find lower bound for dimension D from 2 to 6. We plot that. And if we calculate the total success probability, we can see that with increasing dimension, unsharp measurement gives us a better quantum advantage. Okay. So, okay, this part is not part of the paper, but later we are trying to extend that project and we did some implementation on IBM Q for the previous one. So I shared this one. How we can implement that type of instrument in quantum computer. Okay, so if we have an input quantum state like this, alpha 0 plus beta 1, and we try to implement this unsharp measurement Krauss operator. Okay, here is a tuning parameter theta, and theta is related with eta like this. Eta is equals to cos theta. Okay, so we need a classical outcome for Bob and as well as a post measurement state. So we choose, but in IBM quantum computer, we only perform sharp measurement. Okay, so we choose two state initially. That first one is our initial state and another one is our ancilla qubit. Okay, then this from this barrier to this barrier, this is Bob's measurement. You can see there is a unitary gate acting on that ancilla based on theta, and we then apply a control knot from initial qubit to ancilla qubit to entangle them, and this theta is controlling the weakness of entanglement. Okay, then Bob performing measurement on the ancilla qubit and stored the outcome and pass the actual qubit to Charlie, and Charlie then performs the sharp measurement. Okay, if we do that, then we can see that Charlie always get a correct post measurement state, which Charlie should get analytically using these Krauss operators. Okay, now if we share the data, that these are the raw success probabilities from quantum computer, and after mitigation this turns out to be this. And if we put that in previous upper bound and lower bound formula, we get eta upper and eta lower, and we can see that under noisy condition there is always a finite amount of gap between these two, and these are the experimental parameters what we choose to perform this. Okay, so I would like to conclude this talk here. We propose a sequential communication game with restricted collaboration between two receivers, and the protocol extend the standard 2-to-1 RAC to a prepare, transform, and measure scenario with sequential measurement, we get a non-trivial quantum trade-off between the success probability of two receiver was derived. And using that, we get optimal trade-off point for self-test, Alice's state preparation, and Bob's quantum instrument, particularly unsharp measurement and Charlie's projective measurement. And that enables a semi-device independent robust certification of Bob measurement sharpness. And this result is the upper bound is more tighter than the previously known sequential QRC protocols. There are few possible future direction. There are various, we can implement this in various quantum experimental platforms like photonic system and other devices. And again, we can, here only we certify the unsharp parameter, but this can be extended to the randomness generation and other cryptographic protocols. And extension of the robustness of self-testing to higher dimensional quantum random access codes. And we can also, in our case, we only focus on two outcome unsharp POVM, but people can also certify the more general quantum instrument and measurement incompatibility using this type of sequential game. And this type of sequential game can also be implemented in different type of other oblivious communication complexity tasks also. Thank you everyone for your attention. If you have any question, you can ask.
Thank you, Pritham, for the detailed and very clear talk. Is there any question from the audience? We have time for questions. So if you have questions, please unmute yourself and ask. I think all of the participants have understood everything since the talk was very clear. Okay, there is one question. Can you read it from the Google chat?
Probably question, the request for email address.
Email for PPT.
But this is it a question for you that, yes, why is the Hafnian considered classically
No,
hard?
sir, that was the question for
the last
the
time.
previous speakers.
But it was at showing me 8:45. That was, sir, please share email for PPT presentation. No new question is added.
Okay.
Okay, thank you, Pritham, for your talk.
Okay, thank you, ma'am.
Okay. You may unshare your screen. Okay. So the last talk of this session is by Satyaki Manna from IIT Bhubaneswar. The topic is entanglement assisted communication complexity measured by the distinguishability. Satyaki,
Hello.
over to you.
Hello, am I audible?
Yes, and that's the concluding talk of the meeting also, the entire conference of 5 days. This is the last talk of the last conference. So
you may share your
you may share your screen and give a nice talk to end the meeting properly. That's okay. Can you share the screen?
Yeah, yes.
You just try.
Is it visible?
Yes, it is visible. Go to the full screen mode. Yes, perfect.
Visible. Yeah. Okay. Okay. Hello, hello everyone. I'm Satyaki. Okay. Yeah. I'm Satyaki and I'm from IIT Bhubaneswar. And today I will be talking about entanglement assisted communication complexity measured by distinguishability. And this work is done in collaboration with Ankush Pandit and Dr. Devashish Shah. So before going to the main topic, I am showing you a small example of a communication task that will basically motivate our kind of measure, that is the distinguishability. So traditionally, the communication tasks are measured by the dimension of the message or number of the message. So here we are taking a different kind of measure. So this task will clear how we need this kind of measure. So suppose there is a hospital and that hospital has 4 patients and the patients are characterized by 2 digits. Basically, these can 2 digit, and the first digit denote their blood group, and second digit denote their what drug they are given. Now, suppose some organization comes and they want to do a survey on the patients. What they want to do, they will ask either the blood group of the patient or the drug given to the patient. They would not ask both the quantity at the same time. And what hospital wants to do, like hospital doesn't want to reveal the identification of any patient, but they want to communicate such that surveyor will also know his what they want, and at the same time the identification of those patients are not revealed. So what hospital can do, like these are the 4 inputs that denoted the patient's identity. And they will put a constant on the identity of the patients, that is on these 4 inputs, that is the distinguishability of these 4 inputs. And distinguishability of these 4 inputs are upper bounded by some value, that is q. And on that is can be easily seen that, like, if q is equal to 1, that means these inputs are perfectly distinguishable. Then the receiver can always know the identity of the patients. So this q must be less than 1. Okay. So now we can always write the figure of merit of this kind of task, like giving x1, x2. If y equal to 1, the receiver wants to know the first bit of the x1, x2, that is x1. And if y equal to 2, they want to know the x2. And in this, we have to take all the probabilities, and there will be 8 probabilities, and 1 by 8 is the normalization constant, such that the highest value of s must be less than equal to 1. Now, what we can see, like in classical communication, there is a bound of this success probability with respect to the distinguishability. And if we put q equal to half, success probability will be less than 3/4. But in the same classical communication, and now the parties shared some previous entanglement. In the same classical communication, in this case, with the same q equal to half, we can get s equal to 0.85. That is basically the greater than 3/4. So there is some quantum advantage. So that's imply our the necessity of this kind of measure. And now I am generalizing any 2-party game. Like 2-party means there will be some sender, namely Alice, and receiver who is Bob. And Alice has some input x. Depending on x, Alice will send some message. Message can be classical or quantum depending on the communication. And Bob will have also some input, that is y, and depending on that y and Alice's message, Bob will produce the output z. That is function of both x and y. So we can write the success merit like this, given x, y, the probability of z, and we have to sum over all x, y, z. Now I am going to demonstrate the structure of classical communication. In classical communication, what Alice can do, this is Alice's input x, and this lambda is shared randomness. That is a kind of classical correlation the parties can share beforehand of the game. Now, depending on the x and lambda, Alice will send some classical message. M is here, classical message, classical variable. So Alice, in classically, what Alice will choose some probability distribution for encoding her input to send the message. And similarly, Bob will do the decoding depending on the Alice message M and share into the lambda and his own input y. He will produce the output z. Now, similarly, the condition probability z given xy will be like the rule of classical probability. That will be the multiplication of this encoding probability and decoding probability and the probability of the given lambda, and we have to sum over all the lambda in it. And the constant of the task here is defined as the distinguishability of the Alice's input x, which is reduced to like this. This is max over all the possible encoding probability. Here we define a new variable m prime. M prime basically both m and lambda. Remember that there is no restriction on the number of n. Like in principle, n can be infinite. So any shared randomness can be included into the classical message. So, and it's still we can fix the that will not increase their distinguishability. Okay. So now I'm going to the next class of communication that is called entanglement assisted classical communication. In this communication, Alice will share some arbitrary entangled state with Bob. That is all. And in this case, how Alice will encode his input. Alice can choose any POVM and any quantum measurement, and he will measure her share of entangled state depending on X, and she will get any outcome A. And now, depending on A and X, she will send a message, that is classical message, that is a function of X. And what Bob can do, depending on Bob's input and that classical message M, Bob will do another measurement on his part of reduced state, because Alice is doing some measurement that will steer Bob's state into some another state, and Bob will do the measurement on that part of his state and produce an output J. And the correlation we can find out in the typical bond rule that is given by this. And in this case, the constraint of communication take a very nasty things, nasty something, but what I can see, what I can tell you from here, suppose that this is the classical message Fx. Suppose this is not depending on X and only depending on the outcome of the Alice's measurement, that is only depending on X. So for that case, this communication constraint reduces to the partial distinguishability of Alice's measurement. Why it is partial? Because here Alice choose the entangled state, that is rho AB. In the typical distinguishability problem, we have to maximize over rho AB. Here, no maximization of rho AB is done, because Alice can choose any row like on her disposal. And this rho B is basically the reduced state depending on Alice as a measurement X, and outcome is A. And this probability is coming from the bound rule that is upon Alice's measurement. Okay. Then I'm going to another class of communication task that is called entanglement assisted quantum communication. And here Alice will choose any quantum channel, like any general CPTV map, to operate on her share of entangled state, that is Ex, and send the quantum state to Bob. And depending on the Y and the quantum state Alice has sent, Bob will do any measurement, that is, but in this time there are two states on Bob's side, like one is his own reduced state and another one that Alice has sent to him. So Bob can choose a measurement to operate on both of these states and produce an output J. And similarly, by bond rule, we can see the correlation would be like this. That is basically EX, basically the corresponding crowds of that channel. And similarly, the communication constraint would be the partial distinguishability of Alice's channels. And same thing, the Y is partial, the rho is given, though not maximized over it. And now we can quantify the quantum advantage. So in this work, we are going to show the advantage of entanglement assisted protocol with the classical communication supplemented with shared randomness. And entanglement assisted protocol means both classical communication and quantum communication. So how we can quantify the quantum advantage? We can do it in two ways. Firstly, what we can do, we can fix a certain value of success metric for both the classical communication and entanglement assisted communication, and then find the ratio of this distinguishability, classical by entanglement assisted. So if this distinguish greater than 1, that signifies the quantum advantage. Why? Because suppose we'll get the same success merit, but we need more classical distinguishability that makes classical communication less private. Entanglement assisted communication would be more private. That's why this is this signifies the quantum advantage. But we can define it in other way also, that is the opposite way. We can fix the distinguishability for both the communication, classical intense communication, and find out the ratio of the success probabilities of entanglement assisted communication by classical communication. Here is also same thing. If it is greater than 1, it signifies quantum advantage. And one important result that we derive, that what it says, like if we find advantage in entanglement assisted classical communication, that always implies the advantage in entanglement assisted quantum communication, and vice versa. And the other way around is true also, like if advantage in EAQC also implies the advantage in EACC. So for the rest of the talk, I will show the advantage of EACC with respect to the classical communication, and that always suffices the advantage in EAQC also. Okay, now I am going to a certain class, like a certain task, certain communication task, that is called random access code, and this is nothing but the generalization of our game that I showed in the first slide. Here I am calling it a ND random access code. In the first slide, N and D both are 2. Now N and D can take arbitrary values, and N basically Alice had some N alphabet, and every X can take D number of values. And task of the receiver is same. He has to guess the Y bit when Y is given randomly. So from one of our previous work, we get this bound on classical distinguishability with that classical success probability for the ND random access code. And what we find, like okay, so these two kind of random access code, for 2 to random access code and 3 to random access code, we calculate that this ratio, when the success made is fixed to this value, the ratio is greater than 1. You can see that for 2 to random access code is greater than √2, and this 3 to is some value that is greater than 1. So for these two kind of random access code, we can prove the quantum advantage with entanglement assisted protocol. So then we can go to another different defined communication task. So for that, we prove a more general result that will connect the normal quantum communication to entanglement assisted classical communication. So what we said, sir, that any qubit protocol of quantum communication with Bob executing projective measurements, all these correlations can be implemented in a qubit protocol of entanglement classical communication also. And for this case, the Alice shares maximally entangled state to Bob. So that implies that if we have any advantageous qubit protocol of quantum communication with respect to classical communication, that also suffices the advantage in entanglement assisted classical communication too. So there we also prove some advantage of some other advantageous stuff, that is called graph-based equality problems and pair distinguished tasks. I'm not going into detail of this task. I'm rather moving to a more counterintuitive result. But in this case, there is a communication task. Here, Alice got 3 inputs, that is 1 to 3. But Bob only has a fixed input. Like Bob only do a fixed measurement, only fixed decoding strategy. So Y is fixed, and Bob produce Z. That is, Z also can get 3 values, like 1 to 3. So in this scenario, we can take this success merit, that is in classical success merit, and this is bounded by this thing. That this is written in PZ given X format. And in entanglement assisted classical communication, if we fix the success probability to be this, we prove that this distinguishability ratio would be greater than 1. So this is a counterintuitive result in that sense of that, like without Bob's input, without Bob having any input, we can get quantum advantage, which is not possible actually without entanglement assisted task. So in this case also, we prove that numerically the quantum communication offers no advantage in this kind of scenarios. So we can tell from this, like entanglement assisted task can be advantageous than quantum communication. Now, all these tasks that I showed till now, in all the tasks, Alice shared maximally entangled state to the box. Now our question is, if suppose Alice shares some non-maximally entangled state, can this be advantageous than maximally entangled state? So our answer is affirmative. So for that case, we take another communication task, that is the non-uniform random access code. That is like same random access code, but we like introduce some non-uniformity into this, and there is some this coefficient also non-uniform in the general to random access code. This is the same for all the probabilities. So we make it's non-uniform, and it's the success probability that is a function of theta. All the terms are like given here, like as a function of theta. So now, suppose Alice shares this state. This is a entangled state, but x theta equal to pi by 4. You can see that this is a non-maximally entangled state. So how we can see this plot will demonstrate. Like in this plot, on the x-axis there is theta, and on the y-axis there is two success probabilities. One is classical success probability, and one is entanglement assisted classical communication success probability. And for the both communication, we fix the distinguishability to be half. So what we can see, that is the blue line denotes the classical success probability and red line denotes the entanglement assisted success probability. So what we see that ESCC is greater than SC, and in this region of theta, except theta equal to pi by 4, all the other cases, the non-maximally entangled state gives the highest advantage or highest success probability for this non-uniform to random access code. So these are our main results. Now I am concluding our talk. That is, it's a new approach for privacy preserving communication tasks. It's like especially when the what is share entanglement. It's traditionally the common tasks are measured by dimension, and this is one thing. One new approach is their measure is different, and other thing is with this distinct measure there are some previous papers, but they are only taking the classical communication with the quantum communication where no previous correlations are shared. Here we introduce a previous correlation and find some interesting results. And there are actually can be many future direction. And one interesting scenario one can think of, like Alice doesn't know the PCF entangled state. Some refer your third party is sharing their entangled state, and depending on Alice and Bob doing the communication. And one can introduce some eavesdropper in the scenario, and it's already a privacy preserving communication task with respect to Alice and Bob, and introduce a eavesdropper that might introduce a second layer of privacy, such that like eavesdropper success probability less than Bob. So there one can take this kind of scenario also, and there is no STP or NPA formulations for this kind of task. With this kind of constant, like similar task with dimension constant are already been well studied in semi-technique formulation and other numerical formulations. So this kind of formulations can be devised in this for this task. Okay. So this is our work in the archive. One can take a look into it. And thank you for your attention, and I'm happy to have questions.
Thank you, Satyaki, for your nice talk. Any questions? Are there any questions?
Seems that by the end of the meeting, people have become tired of asking an interaction, but it was full of interaction all 5 days. Means there are many questions. Sometime we had to, today we had a bit, we went a bit relaxed in the sense that some talk when some speaker take less time. So we had space for question on the other days, there were occasions when there were many questions, but we could not allow the interactions. But anyway, let's once again ask, is there any question? Anybody wants to unmute and say something? If not, we just conclude. I would like to thank the last speaker as well as Dr. Indrani Chakraborty for sharing the sessions, and of course, all the session chairs of the 10 sessions. So this
Thank you, sir.
conference happened over 5 days, and there were 10 session chairs, and there are about 42 speakers and participants from almost 9 different countries. So thanks everyone, the participants,
Sir, I will thankful for you for
you want to say something?
organizing
Okay, please
this.
continue.
Sir, I will thankful for you for organizing these seminars. First of all, it was my first international international conference. I attended this. It was very informative for me. And first of all, sir, you was very serious in whole conference, but now I saw your smile. It's very impressive.
So do some
thank you,
work.
sir.
Next time you must be speaker. Next time send the abstract and
Okay, sir. Thank you,
do
sir.
some hard work, and then next time abstract.
Yes.
So
Thank you, sir.
and so apart from the speakers and of course the speakers and the session chairs, the participants deserve a special thank. And because there was a very big constraint of time. Some people are from Far East, means who are very late now, and for some people the starting time was very early. Some people are from US and some people are from Japan. So it's 6 to 9 was a window, means where more or less we could meet. Somebody's little late in evening, somebody is little early in morning. But still, the best part is that every talk happened. Nobody missed the talk. There were many constraints. Even there were constraints from the war situation which is happening in different countries. Some of the speakers were afraid that they may have to go to some place where they will not be able to deliver the talk, or internet will be disturbed. One day there was a rain and internet was disturbing actually in some places in Delhi, but at the end, all well that ends well, and it's ended well. But now, as I mentioned in the yesterday also, that we'll consider this to be successful if this leads to some new collaborations, new ideas out of the box. Means like in a physical conference, many discussion happen. Here it does not happen, but you shared your email, etc. And we hope that next time we'll see some papers where 2 participants of this meeting who did not know each other before this meeting will submit an abstract together or publish a paper together. And so I hope that even the undergraduate students who have joined, they will do their master's students will join for PhD in the related field. And it's a truly interdisciplinary area, so it does not matter whether you are from electronics or engineering, computer science, or maths. So everybody has a bit to do. And with all those things, which will be done in 1 year, with them we'll meet next year once again. So,
sir, would you like to share your experience?
You want to say something?
Sir, would you like to share your experience?
No, I have already told my experience of the meeting and more of my expectations of the meeting. And finally, 2 people deserve special thank. One is Shandip Misra, Dr. Shandip Misra and Dr. Shivani Singh, who managed the entire conference meticulously, and also one set of people whom we have not mentioned who have reviewed the abstracts. We received a large number of abstracts, but only because of the time restrictions, we have to select only 42. So it's not like that the other abstracts were not good, but we had to take opinion of the reviewer, and in very short time period, they reviewed these papers, and we would like to express our thanks for them also. So with all this, I would like to close the meeting now. Thank you all for joining, and keep in touch.